Everyone should recall the law of conservation of energy, as energy cannot be created or destroyed. But this definition is incomplete. The true law is the law cannot be created or destroyed. Energy can only be transformed through work. And work is a concept that is by far the most overlooked when it comes to physics, and it's very, very important. Work is the transfer form of energy. And transferring energy from one form to the other requires an applied force. So what work actually is an applied force pushing an object for a physical displacement. Now the key here is that those two things must be parallel to one another, where the force is parallel to the displacement, or the distance that the object moves. If the object doesn't move, then it doesn't cover a physical distance, and therefore there is no work. However, if there is an applied force for a physical displacement, that object will often gain speed, which is a measurement of kinetic energy. It could gain height, which is a measurement of potential energy, and lots of other forms of energy that could exist. But they all transfer in and out of a system through work. And so work is actually the most dominant form of energy that exists, and we often don't realize that. In this particular case, it's important to note that this is a non-vector, right? There are no arrows above these variables because force is a vector, displacement is a vector, but the amount of energy that a system has is simply a value. And so the positives and negative signs in this case simply indicate whether or not we end up with a positive work or a negative work, which is simply a loss in energy, right? Transferring energy out of the system, or a gain in energy where we are positively adding work to the system. In either case, energy is not a vector, whereas all the other concepts that we've covered so far in this course are. The most basic example is moving or pushing something across the floor. If we had something sitting on the floor, we know that there is a weight force acting down, a normal force acting up. If there is a normal force acting up, that means that this is in contact with the ground. If there is contact with the ground and we attempt to move this crate box forward, then there would be a resisted force called friction acting backwards, which means that in order to move this object forward, we would have to apply a force in this forward direction. If we apply a force diagonally like this, it's important to note that a component of this force is doing the applied force forward, and a component of this force is lifting up. This lift up does nothing to move the block laterally, which means that it does not create a displacement horizontally across the space. So this component of the force does not perform work. Only this component, F cosine theta, where this is your angle theta, generates the work. So as we said before, the work in this case could be the displacement times F times the cosine of theta. And I've said previously, I don't like to lock in that these are the formulas for various concepts with these trig functions built in. Instead, it's important to note that the force must be parallel to the displacement in order for there to be an energy transfer as this system moves across. A similar situation would be lifting an object vertically up. If I have an object suspended in space, we know that it has an F of g acting down. In order to lift up, we would have to apply some force. In this particular case, if we do it with a zero acceleration, we know that this force must be equivalently magnitude of the weight going down. As we lift the object up some vertical height, that displacement is what causes the object, once it's vertically much higher, to have potential energy at the top. We've seen potential energy due to gravity in previous courses as defined mass times gravity times height. When we lift an object up higher and higher and higher, it gains potential energy. Well, the only way for a system to gain potential energy is if there is an active work being accomplished on that object. In this case, this force applied over this displacement yields the potential energy that we have at the top. In other words, the work performed equals the potential energy that this system has once it gets to the top. Similarly, an object falling out of the sky, like a baseball, as the object falls down, its weight is what's causing that to happen. If this is the only force acting on this object and it falls down to the ground, this displacement, d, is the energy that it is transferring from the potential energy that it has at the top to the kinetic energy that it would have at the bottom, which is a function of its speed. Ke is 1/2 mv squared. In this case, the work done by gravity is what causes the potential energy to transform into the kinetic energy at the bottom. Since the work results in a transfer of energy, this is often defined as the net work acting on a system being equal to the change in kinetic energy. This can be demonstrated here where we have a 0 kinetic energy at the top because the baseball has entirely potential energy, and then at the bottom it's moving and it has a sizable amount of kinetic energy. The reason why the ball sped up is that the work performed by the weight has generated a change in kinetic energy. This is referred to as the work-energy principle. And this becomes very useful for a variety of systems where changing velocity, changing kinetic energy, can be described as a function of the force applied on it while that object moves through a physical displacement. In other words, the work.